The topic under consideration is 3D-Bravais lattices. In 1948, Bravais showed that there are only 14 different ways of arranging points in three-dimensional space such that each point has identical surroundings. Here, we are discussing crystal structure. In previous talks, I spoke about 7 standard crystal systems. But later, Bravais has discovered and proved that there are not only 7 crystal systems, but there are few more. That is, he has identified 7 more lattices and added to the existing 7 crystal lattices, forming 14 space lattices altogether. These are known as Bravais lattices. Now to define a Bravais lattice, we take a famous artistic work. Here, if you see carefully, there are patterns which are repeatable. The smallest pattern, which is shown in red, is repeatable, and there is a pattern in green which is repeatable. There is a pattern in blue which is repeatable. The smallest pattern which is repeatable here is defined as Bravais lattice. For instance, if we use the smallest unit cell possible, there are only a certain number of fundamental lattice patterns. These are called Bravais lattices, pronounced like Bravais. In 2 dimensions, there are 5 Bravais lattices, whereas in 3 dimensions, there are 14 Bravais lattices as discussed just now. If we look at periodic table of elements, currently there are 118 elements discovered. So in these elements, whichever are crystalline, when we study those crystalline elements, we come to the conclusion that the lattice structure will be minimized or will be summarized to one of the Bravais lattices. Here a few important points of Bravais lattices are given. Bravais lattices are the foundation for crystal structures. Bravais lattices are the basic lattice arrangements. All other lattices can simplify or can get simplified into one of the Bravais lattices. To summarize, we say Bravais lattices describe the basic crystal structure. Few more details about the basics of 3D Bravais lattices should be known. Each lattice is a polyhedron with 6 faces, 12 edges and 8 vertices. In addition to having a lattice point at each vertex of the polyhedron, there may also be centering. Centering could mean there is an extra atom either at the center of the entire polyhedron, at the center of each of the 6 faces, or at the center of top and bottom faces, which we call as base centering. According to Bravais, the atom can be at the center of the cube, atoms can be on the fixed faces of the cube, or atoms can be on the top or bottom faces. If a lattice had a lattice point at each corner of a cube plus another lattice point at each face of the cube, it would be called face-centered cubic. If the cube had an extra lattice point on the top and bottom faces, not all 6, it would be called base-centered cubic, in short BCC. If the cube had an extra lattice point in the very center, it would be called body-centered cubic. The lattices can have an extra lattice point on all faces, then the notation is used as F for it. The top and bottom bases, then the notation is used as C, or the center, the notation is used as I. If there are no extra lattice points, the lattice is called simple or primitive. In the sense, if there is no centering, then the lattice is called as P, which stands for primitive. By combining the 7 possible polyhedrons with 4 possible centerings and crossing of duplicates, we end up with 14 Bravais lattices. Now to continue the Bravais lattices, I would like to speak of the summary of 7 crystal systems once, which were described in previous video. Here you could see 7 crystal systems names and their lattice parameters and interaxial angles and the examples. When we go for Bravais lattices, we take the beginning 4 columns as it is and we extend them to form 14 because already we have 7 as standard crystal systems. Now if you see, the column of crystal systems is presented as it is, lattice parameters are presented as it is, interaxial angles are also presented as it is, and 7 crystal systems that we have discussed are called as primitive, hence they are mentioned as P. Remember, the last 3, triclinic, trigonal and hexagonal, will not have any centering, so 3 rows here are made yellow. Body centered exist in all the remaining 4, that is cubic, tetragonal, orthorhombic and monoclinic. And one more thing to remember is orthorhombic will have 3 types of centering: body centered, base centered and face centered. This way 7 plus 6, 13 are described. The last one is face centered that exists in simple cubic. The same thing is presented in the form of figures. 7 crystal systems are listed here. Their parameters are listed in this column. Their figures are shown in this column. Since 3 do not have any centering, red dashes are shown here. Then for remaining 4, body centered exist, and also orthorhombic have three kinds of centering. This way we mention three kinds of centering. Here it is written body centered, base centered, and face centered, and what is left is cubic, which has got face centered, other than body centered and primitive.